Dear friends, hello. Today we'll learn about the ER diagram and its components. We know that database design is essentially for deciding tables. For this purpose, we need a tool that allows us to organize the information that we would like to capture in a database. And an entity relationship diagram is such a tool. In short, we say it is ER diagram. So, what is ER diagram? Before discussing about the ER diagram, let's start a brief discussion about the ER model. So, what is ER model? An entity relationship model, in short ER model, is a data model for describing the data or information aspects of a business domain or its process requirements in an abstract way that lends itself to ultimately being implemented in a database such as a relational database. The main components of ER models are entities or things and the relationships that can exist among these entities. The ER model allows us to sketch the database designs, that is, the kinds of data and how they connect. An ER model is an abstract way of describing a database. Look at these two tables in a relational database. First table with table name customer underscore details that stores the personal details of the customers of some telephone exchange. So, each customer has been given unique customer ID stored in the column cust ID along with the personal details of that customer like name of a customer, address of the customer and so on. And in the second table, the information about the telephone connections taken by each customer has been stored. It may be the case that some customers may have multiple connections and thus will have number of telephone numbers for that customers. Both the tables are related to each other through the common field cust ID. In this table cust ID with value 101 has multiple telephone connections whose information has been stored in the customer underscore connection underscore details table. Thus, corresponding to some of the cust IDs in the customer underscore details table has multiple entries in the customer underscore connection underscore details table. Thus, the ER model would tell us that customer is an entity and each phone connection for that customer is also an entity and the relationship between the customer and the phone connections has a connection. Diagrams drawn for designing these entities and relationships are called entity relationship diagrams, or in short we say ER diagrams. Look at the figure shown. This is an example of ER diagram showing the relationship between the entities professor, class and students, which has the relationship with names teaches and takes. Rest of the details about the symbols used here and their purpose we will be discussing shortly. Let us start with the components of the ER diagram. First, we start with entity and entity set. The basic object that the ER model represents is an entity, which is a thing in the real world with an independent existence. We may also say that an entity may be an object with a physical existence, that is, a particular person, car, house, or an employee, or it may be an object with a conceptual existence, that is, a company, a job, or a university course. An entity is represented in ER diagram as a rectangular box enclosing the entity type name. Look at the figure again. There are 3 rectangles in this ER diagram. In those rectangular boxes, professor, class, and student have been written. Thus, 3 entities with the names professor, class, and student have been represented. Each entity has attributes representing the particular properties that describe the entity. For example, an employee entity may be described by employee's name, age, address, salary, and job. Thus, these are the attributes for the entity employee. Again, look at the figure. Here, for the entity professor, there are 3 attributes: HK_ID, name, and office. These attributes are represented with symbol oval, and attribute names are written inside these ovals. These ovals are connected with line with its entity. Thus, in this figure, these 3 attributes are connected through lines with the entity professor. A particular entity will have a value for each of its attributes. The attribute values that describe each entity become a major part of the data stored in the database. The collection of all entities of a particular entity type in the database at any point of time is called an entity set. So, the entity set is usually referred to using the same name as the entity type. For example, a person entity set, a loan entity set. Look at the figure. There are 2 boxes. Each box represents the entity sets customer and loan, consisting of entities customer and loan as its elements respectively. The given figure describes customer and loan entity set. Then we have attribute types. In attribute types, further they may be classified into various categories. First is simple versus composite attributes. Composite attributes can be divided into smaller subparts, which represent more basic attributes with independent meanings. For example, the address attribute of an employee entity can be subdivided into street address, city, state, and zip, with we say the values 2311 Kirby, Houston, Texas, and 77001. Thus, the attribute address is composite. Attributes that cannot be divided are called simple or atomic attributes. For example, attribute employee ID, which cannot be further divided into subparts. So, thus it is a simple attribute. Composite attributes can form a hierarchy. For example, street address can further be subdivided into 3 simple attributes: number, street, and apartment number. The value of a composite attribute is the concatenation of the values of its constitute simple attributes. Then we have the type of attributes as single valued versus multi valued attributes. Most of the attributes have a single value for a particular entity. Such attributes are called single valued. For example, age is a single valued attribute of person. In some cases, an attribute can have a set of values for the same entity. For example, colors attribute for a car or college degrees attribute for a person. Cars with one color have a single value, whereas two-tone cars have two values for colors. Similarly, one person may not have a college degree, another person may have one, or a third person may have two or more degrees. So, different persons can have different number of values for the college degrees attribute. Such attributes are called multi-valued. A multi-valued attribute may have lower or upper bounds on the number of values allowed for each individual entity. For example, the colors attributes of a car may have between 1 and 3 values. If we assume that a car can have at most 3 colors, right. So, then we move to derived versus non-derived attributes. In some cases, 2 or more attribute values are related. For example, the age and the birth date attributes of a person, they are related. For a particular person entity, the value of age can be determined from the current or today's date and the value of that person's date of birth. The age attribute is hence called a derived attribute, and it is said to be derivable from the birth date attribute, which is called a non-derived attribute. Some attribute values can be derived from related entities. For example, an attribute number of employees of a department entity can be derived by counting the number of employees related to the department in which they are working for. So, then we comes to the null value. In some cases, a particular entity may not have an applicable value for an attribute. For example, the apartment number attribute of an address applies only to addresses that are in the apartment buildings and not to the other type of residences such as single family homes. Similarly, a college degrees attribute applies only to persons with college degrees. For such situations, a special value called null is created. An address of a single family home would have null for its apartment number attribute, and a person with no college degree would have null for college degrees attribute. So, thus null can also be used if we do not know the value of an attribute for a particular entity. For example, if we do not know the home or phone of someone, the meaning of the former type of null is not applicable, whereas the meaning of the latter is unknown. The unknown category of null can be further classified into two cases. The first case arises when it is known that the attribute value exists, but is missing. For example, if the height attribute of a person is listed as null. Second case arises when it is not known whether the attribute value exists. For example, if the home phone attribute of a person is null. Now, question here arises in our mind is how to represent an attribute in the ER diagram. That is true. We have already discussed that attribute is connected to an entity and is represented with a oval symbol, but what about the other type of attributes? Let us see. Double circled attributes are multi-valued attributes, whereas dotted oval shows derived attribute. Look at the figure shown. Here most of the attributes are shown with normal oval, but phone number attribute is shown with double circle representing the multi-valued attribute, means customer may have multiple phone numbers. Similarly, age attribute has been marked with a dotted oval represented the derived attribute. Its value will be derived from the current date and date of birth attribute. Now, we move to the ER diagram component, relationship and relationship set. A relationship is an association that exists between two entities. For example, instructor teaches class or student attends class. Most relationships can also be stated inversely. For example, class is taught by instructor. The relationships in an entity relationship diagram are represented by lines drawn between the entities involved in the association. The name of the relationship is placed either above, below or besides the line. Then we come to relationship set. A relationship set captures relationships of the same type. A relationship set is defined between two entity sets A and B. Look at the diagram. Elements of entity set A is related with the elements of the entity set B. Thus, each link is a relationship and the set of all links constitutes a relationship set. Similar to the attributes of an entity, there exists attributes for relationships as well. So, let us look at a relationship set with attributes. Look at the figure. Here depositor is the relationship between the entities, yes, customer and account, and when the customer has accessed the account is recorded in the attribute access date, which is the attribute of the relationship. There are also constraints on the relationship sets. Each and every relationship set is associated with two constraints, and these constraints offer a powerful way to model real world mapping. These constraints are cardinality constraints and participation constraints. So, first is cardinality constraint. The cardinality constraint for a binary relationship specifies the number of relationship instances that an entity can participate in. For example, in any organization, department is to employee is of cardinality ratio 1 to many, meaning each department can be related to numerous employees, but an employee can be related only to one department. The possible cardinality ratios for binary relationship types are 1 to 1, 1 to many, many to 1 and many to many. Look at the figure. Part A of the figure shows husband and wife relationship, which is 1 to 1, as a husband can have only one wife, whereas figure B shows relationship of father and his children, which is 1 to many, as a father can have one or more children. Look at the figure for 1 to 1 representation now. This figure shows a customer can borrow at most one loan, and a loan can be given to at most one customer, and this one to one relationship is shown by drawing arrows on both customer and loan entities. Then is one to many representation. Look at the figure. It shows a customer can borrow many loans, and a loan can be given to at most one customer, and this one to many relationship is shown by the arrow on the customer entity as 1 and a line to the loan entity as many. Look at the figure. Figure A shows child and father relationship, which is many to 1, as many children can have same father, whereas figure B shows relationship of friends, which is many to many. So, now comes to many to one representation. Look at the figure. This figure shows a customer can borrow at most one loan, and a loan can be shared by many customers, and this many to one relationship is shown by a line on customer entity as many and an arrow to loan entity as 1. So, then comes many to many representation. Look at the figure. This figure shows a customer can borrow many loans, and a loan can be shared by many customers, and this many to many relationship is shown by a line on both customer and loan entities. Then another category of constraint on relationship is participation constraint. The participation constraint specifies whether the existence of an entity depends on its being related to another entity via the relationship type. There are two types of participation constraints, total and partial. So, total participation is when every entity in the entity set must participate in at least one relationship. If a company policy states that every employee must work for a department, then an employee entity can exist only if it participates in a works for relationship instance. Look at the diagram. Thus, the participation of employee in works for department is called total participation, meaning that every entity in the total set of employee entities must be related to a department entity via works for. Then comes partial participation. Some entities may not participate in the relationship. We do not expect every employee to manage a department. So, the participation of employee in the manages the relationship type is partial, meaning that some or part of the set of employee entities are related to a department entity via manages, but not necessarily all. Look at the figure depicting both partial and total participation. This figure specifies that some customers may not borrow any loan, whereas every loan must be borrowed by at least one customer. Look at this figure. What can be implied from the participation constraints in this relationship? It can be implied that every customer must borrow at least one loan, and some loans may not be borrowed by any customer. It should be noted here that the given two types of constraints, that is cardinality and participation, are independent to each other. It means that any cardinality constraint can be used with any participation constraint. Now, let us move to the ER diagram component keys. We know what is primary key. Let us revise it. In the entity type customer, we have attribute customer identification number represented by customer underscore ID. This is the unique identification number given by the bank to its customers, right. Thus, the attribute that has unique value and cannot be repeated is called primary key. Moreover, it can never take null value. Now, primary keys in an ER diagram are represented by underlined attribute. Look at the figure. In this figure, the customer underscore ID and loan underscore number are the primary keys for the entity types customer and loan respectively. That is why they have been underlined to give separate identity among attributes of its entity. Then is weak entity sets. The entity sets that do not have primary key attributes of their own are called weak entity sets. Look at the figure. The payment number attribute in the payment entity is not identifiable by its own until and unless we relate it with the loan number attribute of the loan. Because we are not able to know which payment is associated with which loan. Thus, payment entity is weak entity as it is dependent upon the primary key of the entity loan. Thus, weak entity payment is shown in the diagram with double rectangle. Thus, entities belonging to a weak entity sets are identified by being related to specific entities from another entity set in combination with some of their attribute values. We call this other entity set the identifying entity set, and we call the relationship type that relates a weak entity set to its identifying entity set the identifying relationship of the weak entity set. Thus, in the diagram, the loan is the identifying entity set and loan payment is the identifying relationship. A weak entity set always has a total participation constraint with respect to its identifying relationship, because a weak entity cannot be identified without an identifying entity. Thus, in weak entity set, an identifying relationship is depicted using a double diamond. A weak entity set is depicted using a double rectangle. A weak entity type normally has a partial key, which is the set of the attributes that can uniquely identify weak entities that are related to the same owner entity. The partial key of a weak entity distinguishes it from other weak entities belonging to the same strong entity. Here the partial key is underlined with a dotted line. The primary key of a weak entity set is the union of its partial key and the primary key of its host strong entity set. Look at the figure. Here the partial and primary key are shown. Primary key for the payment entity is the combination of loan number and payment number. Let us move to the concept of superclass and subclass. An entity type is used to represent both a type of entity and the entity set or collection of entities of that type that exist in the database. For example, the entity type employee describes the type, that is the attributes and the relationships of each employee entity, and also refers to the current set of employee entities in the company database. In many cases, an entity type has numerous subgroupings of its entities and that are meaningful and need to be represented explicitly because of their significance to the database application. For example, the entities that are members of employee entity type may be grouped further into secretary, engineer, manager, technician, salaried employee, hourly employee, and so on. The set of entities in each of the latter groupings is a subset of the entities that belong to the employee entity set, meaning that every entity that is a member of one of these subgroupings is also an employee. We call each of these subgroupings as a subclass of the employee entity type, and the employee entity type is called the superclass for each of these subclasses. We call the relationship between a superclass and any of its subclasses a superclass subclass, or simply class subclass relationship. Let us move to the concept of inheritance. An important concept associated with subclasses is that of type inheritance. Recall that the type of an entity is defined by the attributes it possesses and the relationship types in which it participates. Because an entity in the subclass represents the same real world entity from the superclass, it should possess values for its specific attributes as well as values of its attributes as a member of the superclass. We say that an entity that is a member of a subclass inherits all the attributes of the entity as a member of the superclass. The entity also inherits all the relationships in which the superclass participates. Notice that a subclass with its own specific attributes and relationships together with all the attributes and relationships it inherits from the superclass can be considered an entity type in its own right. Now, let us talk about specialization. Specialization is the process of defining a set of subclasses of an entity type. This entity type is called the superclass of the specialization. In other words, a child entity has all the attributes of a parent entity, but not the vice versa. The set of subclasses that form a specialization is defined on the basis of some distinguishing characteristics of the entities in the superclass. For example, the set of subclasses secretary, engineer, technician is a specialization of the superclass employee that distinguishes among employee entities based on the job type of each entity. We may have several specializations of the same entity type based on different distinguishing characteristics. For example, look at the figure, each particular employee would be permanent or temporary, and at the same time an officer, secretary or teller Then some of the constraints on specialization are: first is the disjointness constraint, which specifies that the subclasses of the specialization must be disjoint. This means that an entity can be a member of at most one of the subclasses of the specialization. The second is the overlap constraint, that is, the same entity may be a member of more than one subclass of the specialization. The second constraint of specialization is called the completeness constraint, which may be total or partial. A total specialization constraint specifies that every entity in the superclass must be a member of some subclass in the specialization, and the partial specialization allows an entity not to belong to any of the subclasses. Look at the figure. Looking at this figure, we may be able to understand various components of the ER diagram. With this, we come to the end of today's lecture. Today, we have discussed about the ER model and the components of the ER diagram. In the next lecture, we will learn about enhanced ER modeling and the relational data model. Thank you.